Hello all, now we will discuss chapter 2, namely engine design and operating parameters. In this chapter we will study the geometrical relationships for reciprocating engines and then important parameter for engine performance, efficiency and emission. This is the content of this chapter, so we will study or have a quick look for engine characteristic and then engine geometrical relationship, and this is for reciprocating engine, and then forces in reciprocating engine, and then we will list and study each operating parameters for reciprocating engine, and the last topic will be looking at vehicle power requirement. First topic is engine characteristic. There are several important parameters to an engine user, and these parameters control total engine operating costs, and for sure this is the primary consideration of the user. These parameters include engine performance and then engine fuel consumption for sure, and then engine initial cost and initial installation, and then engine noise and air pollution, and also engine reliability and durability. And our focus here will be on the engine performance, engine efficiency and emissions. Engine performance includes what is the maximum torque over the useful engine operating range, and then maximum engine speed and thus maximum engine power. And then the last one is range of speed and torque over which engine operation is satisfactory. Regarding maximum performance, we will have a look for the maximum rated power and then normal rated power. So maximum rated power here means the highest power an engine is allowed to develop for short period of operation, so only for a short period. And then we have a normal rated power, so this is what we usually see in the engine spec. So this is the highest power an engine is allowed to develop in continuous operation. And then what is the speed at that maximum power? It's called rated speed. So this is the crankshaft rotational speed at which rated power is developed. Next one is a geometrical relationship or geometrical properties. The feature on the left side is showing the schematic of 2D drawing for a reciprocating engine. So in this case you can identify we have a piston, so this one, and for sure this one is the cylinder block, and on the upper side we have cylinder head, and this one it's called connecting rod, this one, so this black line. So this is a rod connecting the piston to the crank mechanism. So in this case we have crankshaft with its axis here. Let's take a look one by one on this geometrical parameter. The first parameter is the cylinder bore, and this is represented by a letter B. So B here is the cylinder bore. And then we have a cylinder stroke with a capital L here. So cylinder stroke, I think we learned it in chapter 1. So this is the distance traveled by the piston from top center to bottom center. And then we have a connecting rod length. Here it is represented by a small letter L. Okay. And then we have crank radius, small a here. And we have theta here. This is a very, very important parameter. So this is crank angle, and the unit is in degree. Okay, so you will see later on that a lot of parameter is represented as a function of this crank angle of theta. Okay, and then next one, we have a parameter here. It is S. S here is the distance between the piston pin axis here to the crank axis. And then we have C, small c. This is the distance between the TDC to the piston top surface. So this will be an instantaneous parameter as a function of crank angle. So S and then C here will change with the crank angle with theta. And then for sure we have a BC, TC, and then the next one here is VC. This is the minimum volume of the cylinder or minimum volume of the combustion chamber. You can use either one. Sometimes people always only just call this a minimum volume of chamber. Okay. And then VD is the swept volume. So this is the volume swept by the piston is as it's moved from top center to bottom center. So this VD is the engine volume. So once again, when we talk about engine size of 2 liter, 3.5 liters, 5.2 liters, this is VD. Okay, so and then you might have just single cylinder, you might have 3 cylinder, 4 cylinder, 6 cylinder, 8 cylinder, and so on. Okay, so you can see in here that the piston move up and down. That's why it's called a reciprocating motion. So it goes from TC to BC and then backs again to TC, and then by this crank mechanism, this reciprocating motion is converted into the rotation motion. Okay, so we have piston and then conrod here, and then this is the crank mechanism. Okay, the next one, let's take a look on the parameter related to the geometric. The first one here is compression ratio, RC. So this is also a very important parameter. So when we talk about the engine design and you communicate with your friend or your co-worker, I think one important parameter is what is the compression ratio of your engine design. Okay, compression ratio, I think you already learned about this one briefly in Thermo 1 and Thermo 2. Compression ratio is the ratio of maximum cylinder volume to the minimum cylinder volume. So the maximum cylinder volume occurs when the piston at bottom center. So in this case, the cylinder volume is VC plus VD. Okay, once again, the maximum volume is the swept volume plus the minimum volume, VC plus VD. The minimum volume is VC. So therefore, we have equation 2.1 for the compression ratio. And then the next parameter that is also important for designing an engine is the ratio between bore to stroke. Other people use the inverse one, so it's stroke to bore. It doesn't matter. So equation 2.2. So RBS. So this is the ratio of the bore to stroke. Okay. And then the next one, equation 2.3, R, capital R here, is the ratio of the cone rod length to the crank radius, small l over A. Okay. And then you can see in here from this crank mechanism schematic that L, so this is the stroke, equals to 2A. Okay, so when the piston at TDC, so L, so it's mean we don't have L there. So we have the position of the crank at this location. Let's put it 0. And then as the piston move down from TC to BC, so it's mean the piston travel by the stroke, then the position of this O move to this one. So this is O when the piston at BC. So it's mean you can see in here the distance between, let's say this is O1, this is O2. The distance between O1 and O2 here is 2a, okay? And this 2a equals to L, capital L, okay? Therefore, we have this correlation. This is the typical number that we have right now for compression ratio. First one here is for SI, so this is spark ignited engine. So we might have a gasoline engine or natural gas engine. So currently the compression ratio for spark ignition engine is between 9 to 12. Okay, and then I think right now we are also doing a kind of research looking at around still 12, so 12.5, something like that. And then natural gas spark ignited engine can have a slightly higher compression ratio. And right now we are doing a research for natural gas engine looking at compression ratio close to 13 to 1. But you know, it's still kind of research. We need to check whether our design is good to go or we have an issue with knocking and we need to redesign the engine or we need to reduce the compression ratio. And then the next one, this is the range of compression ratio for compression ignition engine. So you can call it diesel engine. So we know that the diesel engine doesn't have any issue with knocking, so that we can push up this compression ratio. So the range is right now is between 14 to 22. So this upper range might be too optimistic. So right now for the heavy duty compression ignition engine, we have compression ratio I think close to 19 to 1. And then I believe last year we have done a kind of short research looking at the compression ratio of 22 to 1. But for this high compression ratio, we need to have a different material for cylinder head because of the peak cylinder pressure increase. The next one is RBS number is between 0.8 to 1.2. This is for small and medium engines. And then this number drops to around 4.5 for large slow speed compression ignition engine. So I think I already mentioned to you in short way that the engine speed is controlled by the piston speed, and this piston speed, you will see later on in the next slide that this piston speed is controlled by the length of, or controlled by the stroke. So it's mean that if we have a larger stroke, we need to reduce the engine speed to maintain the same piston speed. So therefore you will see the trend for the engine speed that it has a lower number for a larger engine speed. So, and the reason for this is that we need to control the piston speed to avoid intake choking. So we'll learn this in more detail in chapter 6. And the next one is the range for R. So R here is the ratio between the connecting rod length to the crank radius. So R is between 3 to 3.5, and this is for small and medium sized engine. And then for large slow speed compression ignition engine, so diesel engine, so R can be between 5 to 9. Next equation is the cylinder volume. So this is instantaneous cylinder volume, V. V is the sum of Vc plus the volume swept by the piston as it's moved from Tc to a certain position. And the distance from Tc to the certain position is C. Okay. Therefore, the volume swept by the piston is the cylinder volume with the height of C, and then the area of the cylinder cap here is the circle area with the diameter of B, so capital B. So equation 2.4. And then equation 2.5, here is the formula for S, small s. This is the distance between the piston pen axis to the crank axis. This equation is derived, I think, with the aid of Pythagorean theorem. So you can add an additional line here, okay, and then let's say the distance between, I put this one is, maybe put it's x1, this one x2, this is x3, okay. So I can say that between x1 and x2 here, I put the distance s1, and then between x2 and x3, the distance is s2. So I have s equal to s1 plus s2, okay. So I know that s2 equals to, here is a cos theta. So once again, theta is the crank angle. And then S1, you can use the Pythagorean theorem. Here we have L square equals to, let's say I put here, maybe what's here? Let's put this one is S3. Okay. L square here equals to S1 square plus S2 square. S3 square. And then I know that S3 here equals to A, and then sine theta. Okay, and then you can substitute this S3 with this one, and then you can replace S1 by this correlation. Then you should be able to get this equation 2.5. Okay. The next parameter here is C. So C is formulated by equation 2.6. So this is derived from the fact that C here equals, okay, C equals to A plus S. Okay, C equals to A plus S. So minus, no, not A equal plus S. A plus L minus S. Okay, yeah. So when the piston is at TC, so it's mean here that S equal to A plus L, so that C equals to 0. This is just a quick check whether this correlation is true or not. So then if we substitute S by equation 2.5, you will get 2.6, and this is for C equation. So you can see in here that S is formulated as a function of crank angle, and then C is formulated as a function of crank angle as well. And you know that L, small l, is a constant, and then small a is a constant. So once again, we can draw S and C here as a function of crank angle. So at top dead center, the crank angle is 0, and then at bottom center, the crank angle is 180 degree, and then when it's go back again to top center, to the next rotation, the crank angle is 360 degree. Or it's back to 0 when we talk about two-stroke engine, because it's complete one cycle. Okay, equation 2.8 here is showing the equation for the cylinder chamber area. So this area is very important when we deal with engine heat transfer. We will learn this in chapter 11. So area of the cylinder chamber here is the sum of the cylinder head area. So if you have a simple flat cylinder head like in this schematic, then the area of the cylinder head is just pi times b squared over 4. But you will see that actual engine doesn't have such a simple cylinder head profile. So AS equals to ACH, so this is the cylinder head area, plus AP, this is the piston top surface area. So you will see also that the actual piston surface is not flat. It might have some valve pocket to avoid interaction with the valve or collision with the valve. And then the last one here is the area from the cylinder liner. So this is a function of C. Okay, so equation 2.8 here is the one for the cylinder chamber area. And then equation 2.9 here is the same as equation 2.8. So in this case, we substitute C with equation 2.6. So you can see in here again that the cylinder area is a function of crank angle. The next parameter is piston mean speed, and this is actually the important parameter, or the parameter that controls the engine performance, not the engine rotation speed. Okay, so piston mean speed is formulated based on the fact that the piston need to travel from TC to BC and then back to TC, so it's mean 2L, to have a complete one rotation. So it's mean here the crank will rotate for a complete one rotation. So from TC back again to TC. Therefore, we have this correlation 2L times N. N is the crank rotation or the engine rotation speed. Okay. Then the next one is the instantaneous piston speed. So to get instantaneous piston speed, we need to derive the piston position formula to the time. So we have a piston position represented by C or represented by S. Okay, so let's say we pick up this S equation, so 2.5 here. If we derive this equation 2.5 to the times, we will get equation 2.12. Okay, so this is the instantaneous piston speed, and it is normalized to the piston mean speed, this one. Okay, and the next one is the instantaneous piston acceleration. So this is obtained by deriving or applying the derivation of equation 2.11 here to the times. So you derive the velocity equation to the time, then you will get equation 2.14. Okay, so you can see in here equation 2.13, this is for the instantaneous piston speed, and equation 2.14, this is the instantaneous piston acceleration. Both are a function of a crank angle, so theta. So we can make a plot of this instantaneous piston speed and instantaneous piston acceleration as a function of crank angle, and this is shown in this figure. So we have a crank angle of 0 here, so this means that the piston is top dead center, and then this is at 80 degree, so this is when the piston at bottom center, and then 360 degree is when the piston is back to top center again. So the first one, this is the plot for, let me put this is blue. So this is the plot for C over L. Okay, C over L. So C equals to 0 when the piston at top center, and then C equals to L when the piston at bottom center. That's why we have value here of 1. So C over L equals to 1. Okay, this is when the piston at bottom center. Okay, and then the next plot here is, let's say here purple, is the instantaneous piston speed. So this one, so the purple line here. Okay, sorry, it doesn't coincide. Okay, so this is the instantaneous piston speed normalized by the piston mean speed. So the piston speed is 0 when the piston at top center, and then it increases. And what is important here is that the maximum piston speed is not halfway between TDC and BDC, but it happens before 90 degree. So you can see here. Okay, so this is the maximum piston speed. Okay, and then the piston speed is 0. Okay, piston speed is 0 here when the piston is at bottom center, and then it's negative because the direction change here, and then it has a maximum or minimum number here. It is after 270 degree crank angle, and then specs to 0 when the piston is at top center again. Okay, and then the last one here is the instantaneous piston acceleration. I use a red line here. So we can see here that the piston acceleration is not 0 when it is at top dead center firing, and then it is 0 at the point of the inflection for the piston speed. So it means this one is 0. Okay, this one is also 0. So this instantaneous piston acceleration control the inertial force generated by this reciprocating motion, and we will see later on what will be the shape of the torsion and so on. In practical reciprocating engine, there are two modifications that can be applied. Number one here, what is called a piston pin offset. So in this case, the piston pin axis is offsetted by certain amount from the crankcase axis. So in this case, we have a Z. So for clockwise rotation, like this one, the piston is shifted to the left with the amount of Z, and Z here can be certain percent of the engine bore. And then the second modification here, what's called crankshaft axis offset, or Y. So same thing here, the crank axis is shifted to the left of the piston axis by by Y, and this Y can be a certain percent of the engine bore. The purpose of this modification is to reduce engine mechanical stress, and therefore we might be able to have a lighter material of this chamber, which ultimately improve the engine efficiency. Next subtopics is forces in reciprocating engine. So the feature on the left side here is showing the schematic of the reciprocating engine along with forces acting on it. So let's take a look one by one. So in this figure, we assume that the piston is moving down toward a bottom center. So we have a combustion inside the chamber generating a high gas pressure, therefore it generates a force acting on the top surface of the piston. It is represented by this sign. Okay, so this is the cylinder gas pressure. So the force here is P, so this is gas pressure times AP. So this is the piston area. So this is the upper side piston area. And then on the bottom side, on the underside of the piston, we have the force due to the crankcase pressure, so PCR. and the direction is opposite to the gas pressure from the upper side. Okay, and the force acting on the underside of the piston here is PCR times AP. So in this case, we assume that the upper side area equals to underside area. Okay, and then other force here is for sure friction. So there is a friction between the piston rings to the liner. So this one. And then we have also a reaction force from the liner, so RL here. So L, I believe this is, I think stand for the longitudinal, so this is the horizontal force. And then we also have a reaction force from the connecting rod. So this is RC, okay? And then the angle between the connecting rod and the vertical line here is a phi, okay? And then in the crank mechanism at this point, so the force perpendicular to the crank radius here is RC tangent, and this is RC time sinus of phi plus theta. Okay, so now let's apply an axial force balance. So then we will get equation 2.15. So on the left side, this is the inertial force of the piston. So this is the piston mass. So in this case, the mass of the piston itself plus the mass of the connecting rod upper part. And then times AP. So this is instantaneous piston acceleration. So we already had this correlation in the previous slide. It is balanced by the sum of all forces in the axial direction. So we have this one is the gas pressure from the top, and this is the crankcase pressure multiplied by AP, and then minus F. So this is the axial force due to the friction, and this one is the reaction force acting on the connecting rod. So this is RC times cos phi, because this is this axial. So let me put like this one. Okay, and this is RC time cos phi. Okay, so we have this one. Okay, and then similarly we can apply the force balance for the other direction. In the horizontal direction, we will get equation 2.16. So RL equals to RC times the sinus of phi. And then the torque generated by the engine, so this is at the crank mechanism, so this is equals to the arm length, so this is the crank radius, times this one, RC times sinus of phi plus theta, equation 2.16. And then you can apply one of the mathematical correlation for this sinus of phi plus theta. So you will get this correlation, and if you substitute this correlation to equation 2.17, you will get the torque equation here as a function of crank angle. So equation 2.18. So once again, with this correlation, you can make a plot of the engine torque as a function of the crank angle. This is an example of the plot for the gas pressure. So we have a peak cylinder pressure after TDC. So this is due to the combustion. And then we also have a friction contribution here that lower this cylinder gas pressure. And then this is the level for the crankcase pressure. And then this is the plot for the sinus theta. So theta here is the crank angle. So starting from minus 180 here, so it's mean the piston is at bottom center and then move up toward top dead center. So theta will be at 0 and then move back again to the bottom center. And the last one here is the plot for the torque. Okay, so the torque is maximum when the cylinder pressure is maximum. So this point is at peak cylinder pressure. and the torque is very low here initially, and then it's going negative, and then there will be a change of the torque sign here at top center, and then it's max once again at the cylinder pressure maximum point, and then it's going zero again somewhere here, and then drop to negative. This feature is showing the schematic for the impact of the force to the cylinder blocks. So in this case, we assume that the crank rotation is in the clockwise direction. So on the first feature on the left side here is when we have a combustion. So it generates a high gas pressure, and it's push the piston down toward bottom center, and then there will be momentum or energy transfer here from the piston to the crank mechanism through this conch rod, and there will be a reaction force in the direction of the liner going to the left. So, and the force acting to the liner here generate a load, and this is called a major thrust load. Okay, and then when the piston move up toward top center, this is represented by the feature on the right side. For example, this is during the compression stroke. Then there will be a force acting to the cylinder liner, and the direction is going to the right, and this will generate a load to the cylinder liner, and this is called a minor thrust load. And the effect of the piston pin offset is to shift the change of this minor to the major thrust load earlier, okay, so that it reduces the stress to the cylinder block. And for sure, if you can reduce the stress, mechanical stress to the cylinder blocks, we can have maybe a cylinder block design with a lighter material, and thus it will reduce the inertial force or inertial mass, and thus it will improve the engine efficiency. Next, let's take a look on the engine operating parameters. The first parameters we'd like to see here is engine brake, torque, and power. Engine torque is normally measured with a dynamometer. So in this case, the engine is clamped on a test bed, and the shaft is connected to the dynamometer rotor. So this figure illustrates the operating principle of a dynamometer. So we have a rotor that is coupled electromagnetically or hydraulically or by mechanical friction to a stator here. So we have a rotor, we have a stator, and then the stator is balanced with the rotor stationary, and then the torque exerted on the stator, so with the rotor turning, is measured by balancing the stator with weight, spring, or pneumatic means. So by looking at this figure, so we know here that the torque is F, so this is the force, times the length of the torque arm, so in this case is V. So equation 2.16, okay? And then the power delivered by the engine, and for sure it is absorbed by this dynamometer, is the product of the torque and engine angular speed. So we have torque here, so this equation 2.20a. So this is the equation for the power as a function of the torque and then engine rotation speed, and it's multiplied by 2 pi here to convert from this rotation speed unit RPM into the radian base unit. And then there are two additional equations here. This is just to help us calculating the power for a different unit. So in case you want to have the engine power in kilowatts, so in this case you can use the engine speed in terms of rotation per second. So this is usually, it's called RPS. But the popular unit that you see in your engine dashboard, usually this RPM, so rotation per minutes. So you need to divide by 60 to convert from RPM to RPS. And then torque unit here is Newton meter, and then we need to multiply it by 10 to the power of -3 to get the power in kilowatt. And the last equation here is in case you want to get the power in horsepower, HP. So we have engine speed in RPM, so and then torque in pound-force times feet, and then divided by 52. Okay. Next one is indicated work per cycle. So pressure data for the gas in the cylinder can be used to calculate the work transfer from the gas to the piston and vice versa. Okay, and we learn about this one in Thermo 1 as well as Thermo 2. So this figure is showing a plot of pressure and volume. So this is called a PV diagram. Okay. On the left side, we have the PV diagram for the two-stroke engine. So EO here is the exhaust valve opening, and then IO is the intake valve or intake port opening. So in the two-stroke engine, just to repeat again, we have a compression process. So it's been going to the left, so the piston move up toward top center, and there will be a combustion here that increases the cylinder pressure up to this level. And then there will be an expansion process, okay, expansion stroke, and then at some piston position, the exhaust port open, so there will be an exhaust process, okay. So the gas exiting the cylinder because of the huge pressure difference between the cylinder and the exhaust manifold. And then at certain position before hitting a PTC, the intake port open, so there will be a scavenging process. So this is used to help further pushing out the exhaust gas from the chamber. And then while the fresh mixture is inducted into this chamber. So and then this will be a scavenging process, and then back to the PTC. The feature in the middle here is the PV diagram for the four-stroke natural aspirated engine. So we will study this in more detail about this naturally aspirated engine, as well as this one is turbocharged engine in chapter 6 and 7, I believe. So this natural aspirated engines means that the engine doesn't have a turbocharger, and the fresh air induction to the engine is mainly due to the pressure difference between the intake manifold and the cylinder pressure. So in this naturally aspirated engine, we have an intake process here. So from this point going to this point, and then the exhaust stroke occurs from, let's say, this point going to this point again, following this arrow. So this one is for the exhaust process, let me put E, and this one is for the intake process. So the main important thing here is that the intake pressure is lower than the exhaust stroke pressure. Okay, and because of this condition, then there will be a negative work. So you can see there that the process line arrow direction is counterclockwise. In Thermo 1, we learned about this one. If you have a process in the direction of clockwise, so we will have a positive work. So like this one, so this is a positive work because of the clockwise process direction. So you see here. Okay, so in this case we have a negative work because of the intake and exhaust stroke, and then we have a positive work. So this is colored by this blue because of the compression and the power stroke process. Okay. And then the feature on the right side here, this is the PV diagram for the 4-stroke engine with a turbocharger. So when the engine is equipped with a turbocharger, the intake manifold pressure is increased so that it is higher than the exhaust manifold pressure. And this will result in increased cylinder pressure during the intake stroke compared to the cylinder pressure during the exhaust stroke, represented by this feature. So this one is for the intake stroke. So you see here, the pressure line is above this pressure line, and this is during the exhaust stroke. Okay, so now you can see that the direction of this process line is clockwise. It means it makes a positive work, and this one is also still make a positive work. So from these two features, you can see the benefit of having turbocharger in the engine, namely to increase the power of the engine. Okay, and then we can calculate the work, and this is indicated work. Why it's called indicated? Because this power used to be measured or to be got directly from an engine indicator. So if we integrate this PV diagram from starting point to the end is, it means it's back again to the initial point because it's a cycle process. We can apply this equation 2.21. So this is, you can see in here, this is the ring sign. So it's mean the integration is from the first point going back again to the first point. So this is integral P dV. So because of these two different conditions between B and C, okay, so the first one here is naturally aspirated engine, second one is turbocharged engine. So we have two different indicated work here. Okay, we have two different indicated work here. The first indicated work is called indicated gross indicated work, and this is per cycle for sure. This is a work delivered to the piston over the compression and expansion stroke only. Okay, only. So once again, this over the compression and expansion stroke only. So this is the blue color in the picture in the middle. Okay, and then the next one, it's called net indicated work. So this is work delivered to the piston over the entire 4-stroke cycle. This one, so over the entire stroke cycle. So it means it's the netto of the work, and this is the work that is transferred to the piston. Okay, and then from the piston is transferred to the crank mechanism. So later on you will have a different parameter for each of these indicated work. For example, for the gross, we will have what's called gross IMEP. I think I've introduced this IMEP in Thermo 1 and Thermo 2. So I here is indicated, and then M here is mean, and then E is effective, and then P is pressure. So we'll have more information about this MEP the next slide. And then if it is net indicated, then we have NIMEP. Okay, so and here is net. And then you will see also later on we have also pumping work. So this is the work required. Okay, so in this case it's only for naturally aspirated engine. So you have a negative work. So it's mean the gas need to have a work from external source. So in this case the piston. And then if we have a turbocharged engine, then we will have a positive pumping work. So in this case the gas will do a work to the piston, as shown in figure C here. And this pumping work is the work during the intake and exhaust process. So once again, if we have a naturally aspirated engine, the pumping work transfer will be to the cylinder gas, okay? And this is because the intake stroke pressure is less than the pressure during exhaust stroke. And we have a positive pumping work if the engine is equipped by a turbocharger, and the pumping work will be transferred, okay, from the gas to the piston. Okay, so this is an additional work besides the work during the compression and expansion strokes. This feature helps us understanding the differentiation between indicated work and then brake work. So indicated works here, assuming that we have a net indicated work. So this is the work transfer from the in-cylinder gas to the piston. So this is the work, okay? And then the usable work, so this is the work that is used to propel this crank mechanism. So this is called brake work. Okay, so this is called brake works. So the difference between the indicated work and the brake work is the work losses from this one to this one. And this is the friction for sure. So this is because of the mechanical friction. And then it's also work to drive essential accessories. So we might need to drive the fuel pump, and then you might need to drive the fan, and then others and others. Okay, and then if we have a naturally aspirated engine, so we can. Next one is mechanical efficiency in natural aspirated engines. So a part of the indicated work per cycle or power here is used to expel exhaust gases and to induct a fresh charge. We also need work here to overcome friction of the bearing, piston, valve train, and so on, and as well as the work to drive the essential engine accessories, so fuel pump, fan, and so on. So all of this power requirement are grouped together and called a friction power. Once again, in real application, usually we don't include this one into the friction work, but to avoid confusion with the one from the book, I think in this class, let's put this pumping work into the friction power as well. So this friction power, once again, is the sum of the pumping work, which is negative for naturally aspirated engine, plus the work to overcome the friction of the bearing, piston, valve train, and so on, plus the work to drive the essential engine accessories, so fuel pump, fan, and so on. Then we have equation 2.23. So in this case, the indicated power is the sum of the brake power. So this is the power outputted by the engine. So this is the available power of the engine for doing something else. For example, to be coupled with the dynamometer and measure it, and then or to be coupled for different purposes. Okay. And this one is the friction power, including once again, including the pumping power. So I think in chapter 12 we will talk a bit about this friction power in more detail, but how do we measure the friction power, and one of the method is by motoring the engine. So in this case we drive the engine with external source, for example using electric motor and so on. And then the ratio of the brake or useful power delivered by the engine to the indicated power, it is called mechanical efficiency. So this is the ratio of PB over PIG. So once again, this we use a gross here just to follow the convention in the book. So although in real application usually we have PB over PIN. So this is the net. So because we don't include pumping work into the friction work, okay, or we can write it down here as 1 minus PF over PIG. So typical mechanical efficiency at wide open throttle valve is 90%, and it can drop to 75% at high engine speed. And what will be the mechanical efficiency at the idle operation? I think you can guess it. Okay, it is 0, because we don't have the brake power at idle operation. You just turn on the engine and it's rotates, the crank mechanism rotates, but it doesn't generate any brake power. Therefore, mechanical efficiency at idle operation is 0%. The next parameter is mean effective pressure. As I mentioned to you, we have learned about this parameter in Thermo 1 and Thermo 2. So a more useful relative engine performance measure is obtained by dividing the work per cycle by the cylinder volume displaced per volume. So when we talk about the engine torque, when we talk about the engine power, it's depend on the engine size. So in this case, we want to have a parameter that is independent of the engine size, and this is mean effective pressure. Okay, so this is the formula for the work per cycle. So we have a power and then an R here. It is the crank rotation number per cycle. So it is 1 for 2-stroke engine and 2 for 4-stroke engines. And here is the engine rotation speed. So the MEP here is the work per cycle per cylinder volume displaced by the piston. And we have equation 2.25a. So this is P times NR divided by VD over N. And we have two other correlation here just to help us to get the MEP to a certain unit. So if you want to get in kPa, so we have power in kilowatt, and then multiplied by 1000, and then VD is in decimeter cubic, so this one is liter. So 1 cubic decimeters equal to 1 liter, and the engine speed is in RPS, so revolution per second. Or if you want to get the MEP in British unit, we can use equation 2.25c. So in this case, the MEP is in pound force per square inch, and then the power is in horsepower, and then an R here either 1 or 2, and then multiplied by 396,000 divided by the engine displacement. So this one is in a cubic inch, multiplied here by the engine rotation speed. So in this one we have RPM. So we have MEP here, depending whether P here is gross or net or brake, then we can have GIMEP, or we have net IMEP, or we also have brake MEP. Can we have the friction IMEP? Yes, then we have FMEP. So in real application, as I mentioned to you once again, usually we also have PMEP, but in this book we include this PMEP into FMEP. So this is what we have for the BMEP. So in this case, BMEP is a function of the engine torque, and then this is the engine displacement, and R once again either 1 or 2. And then this is the BMEP in British unit. So torque here is the pound force times width, and then the engine displacement is in cubic inch. So usually base BMEP at max torque and max power is established. So if you just Google like GM Ecotec or any engine from Ford or from Toyota or any company, usually they include this spec. So what is the PMEP at max torque, and then what is the max torque itself for sure, and then what is the max power. So this PMEP represent how effective the displaced volume is used. So it means if you design an engine and your engine can operate at higher PMEP, so it means you have a more effective engine design. Okay, and this is the typical BMEP for different engine types. For naturally aspirated spark ignited engine, so the PMEP is between 10.5 to 12.5. So this is the best PSPMEP. And then when including a turbocharger in the engine, then we can increase the PMEP. So in this case, we have the PMEP range from 18 to 24 for turbocharged spark ignited engine. And this is for naturally aspirated compression ignition engine, so diesel engine. And the last one here is for turbocharged diesel engines. Let's take a look on this simple example to help us understanding the correlation between these several parameters. So we have a 4-cylinder, 4 valves per cylinder, naturally aspirated automatic spark ignited engine. So 4 valves, so we can assume 2 valves for intakes and 2 valves for the exhaust. So in this case, the engine is being designed to provide a maximum torque of 195 Newton meter in the medium speed range, so in this case 4000 RPM. The question is the estimated required engine displacement, bore, stroke, and maximum brake power the engine will deliver. Let's take a look on the solution of this example. First, we need to assume what is the targeted PMEP. So let's take a 12 bar, so this natural aspirated engine. So we use equation 2.26a here. And this equation correlates a PMEP to engine torque and engine displacement. So engine torque is given, so 195 Newton meters, and we target PMEP of 12 bars. Then we can calculate the engine displacement, and we get 2 cubic decimeter, which is 2 liter. Okay, let's assume we have a 4-cylinder engine. So let's say this is 4-cylinder inline. Then we can calculate what is the bore and stroke. So let's apply also another assumption that the bore equal to the stroke. So it means it is a box engine. So we have this correlation. This 4 represent the number of the cylinder. Then to get the total volume of 2 liter, we have a bore and stroke of 86 millimeters. This is box engine with 86 millimeter. I believe this is Ecotec engine. You can check it. Okay, this is Ecotec engine from GM. So Ecotec 2.0 liter. Okay. The next one, we assume the maximum mean piston speed. So let's take a 17 meters per second. So once we fix this maximum mean piston speed, we can get what is the maximum engine rotation speed by using this correlation. So the piston mean speed equals to 2 times L time nx. So L here is the stroke, 86 millimeters, and this is the assume maximum mean piston speed. Then we get the maximum engine rotation speed, 99 RPS, and then you need to multiply it by 60 to get RPM. So 5,900 RPM. Okay, so you need to check with your engine, especially for you who is driving GM engine. So you can check whether your maximum engine speed is 5,900 RPM, assuming your car is using Ecotec 2.0 liters. The next one, assuming PMEP at max torque is 10% lower than the PMEP at max torque. So we'll talk this one in more detail in the next slide. So in this case, we assume that the PMEP at maximum power is 10% lower than the PMEP at max torque. Why it is lower? So this is because of the increased engine friction and wall heat transfer, I believe. So assuming that once again that the PMEP at max power is 10% lower than the PMEP at max torque point, then we can calculate the maximum power. So in this case, the PMEP is 0.9 times 12. Okay, so we have 1080 here, and then we have the volume 2 liters, and then the engine rotation speed and RPS is 99. And then an R here is 2 because this 4-stroke engine, and you will get the maximum power of 107 kilowatts. What is your engine maximum power? So check it whether it is around this one. The next parameter is specific fuel consumption and efficiency. So in engine tests, the fuel consumption is measured as the fuel flow rate or the mass flow rate per unit time. So in this case, we have MF. Okay, and then we have a parameter called a specific fuel consumption, SFC. So this is the ratio of the fuel mass flow rate over the power output. So equation 2.27. Okay, so this is one of the parameters to represent how efficient the engine is, depending on whether P here is gross or net or brake. So you might have ISFC if it is indicated, or you might have BSFC. Okay. The next equation here is to help us to get SFC in different units. So this one is in milligram per joule. This one is in gram per kilowatt hour. Okay, so this is the most popular unit. If you want to get the unit in British unit, then you can use this equation 2.28c. You don't need to remember this equation. So in the exam, I will list all equation needed to solve the problem. The second parameter to represent engine efficiency is thermal efficiency. So this is the ratio between the engine work to the fuel energy, or if it is formulated in a power parameter, then we have a P over M dot F. So this is the fuel mass flow rate times QHV. So this is the lower heating value of the fuel. I think we have discussed this lower heating value along with higher heating value in Thermo 2. So depending on whether P here is indicated or brake, you might have ITE, so it means it is indicated thermal efficiency. You might have a PTE, so if it is brake, so this is PP, then this is a PR. And then how does this thermal efficiency correlates to the specific fuel consumption? So we have equation 2.30a here. So the thermal efficiency is 1 over SFC times QHV. So the correlation is controlled by the fuel lower heating value, or I can write it down here is that SFC equal to 1 over thermal efficiency times QHV. So from this correlation, you can see that if you replace the fuel of an engine by the one with higher heating value, then you will have less specific fuel consumption. It means your engine requires less fuel amount to conduct the same output power. This makes sense. So this three equation help us to get the thermal efficiency as a function of the specific fuel consumption and lower heating value at different units. So this one is in case we have SFC in milligram per joule, and then the lower heating value is in megajoule per kilogram. And the last one here is for the previous unit. This table is taken from the appendix of Thermo 2 book, so from Moran Sapiro. This one is showing the lower heating value for different fuel. So you need to stay attention on this column. This is the lower heating value of gasoline. For example, we have 43 megajoule per kilogram. And then methane, here is the main component of natural gas, so it has 50 megajoule per kilogram. How about ethanol? So ethanol, it has only 26.9 megajoule per kilogram. So you know that all gasoline sold in the US contains about 10 to 15% ethanol. Therefore, in the fuel station, you might see A85 or E90, so it means this one has 15% of ethanol, and this one has 10% of ethanol. The next parameter is the air-fuel ratio. So the definition is straightforward. So air-fuel ratio is the ratio of the air mass flow rate to the fuel mass flow rate, so equation 2.31. We can also use this second correlation. So this is fuel air ratio. So this is the ratio of the fuel mass flow rate to the air mass flow rate. And we have additional parameter. First, it's called phi. So this is the ratio of the stoichiometric air-fuel ratio to the actual air-fuel ratio. I think we learned this one in chapter 3. And then we also have a lambda. So this is the inverse of phi. Okay. So in Thermo 2, I believe I introduced this phi. So we have a rich mixture when phi is above 1. So it means you have more fuel than the theoretical amount of the fuel. So we have a lean mixture when phi is less than 1. So it means we have more air than the theoretical amount of air. The next parameter is volumetric efficiency. The intake system of an engine, which is usually consisting of intake manifold. In this case, we have a plenum. So this is the intake system of the engine. So it's consisting of the intake manifold or plenum, and then might be air filter, and then intake runner, intake valve, and so on. Restrict the amount of air which an engine of a given displacement can induct. And the parameter that is used to measure the effectiveness of an engine induction process is called volumetric efficiency. And this volumetric efficiency is only applicable to 4-stroke engine. The volumetric efficiency is defined as the volume flow rate of air into the intake system at a defined air condition divided by the rate at which volume is displaced by the piston. So we have this correlation. So volumetric efficiency here is a function of the air mass flow rate over this parameter. So this is the density of the air intake, and then phi d is the swept volume or the displacement of the engine, and here is the engine rotation speed. Or we can formulate it with the second equation. In this case, we remove the unit of times. So depending on where is the location of the air density, either this volumetric efficiency represent the effectiveness of the entire system, entire intake system, if the air density is the ambient air density, or it's represent the effectiveness of, let's say, intake runner and intake valve if this air density is taken at the intake manifold. So downstream of the intake manifold, we have intake runner, intake port, and the intake valve system. Next parameter is specific power, specific weight, and specific volume. Specific power here is the ratio between the engine power to the engine displacement, so equation 2.34. And then specific weight is the ratio of the engine weight and maximum power, and specific volume is the ratio of the engine volume to the maximum power. So for this parameter to be useful in engine comparison, we need to have a consistent definition of what component and auxiliaries need to be included when estimating or calculating the engine weight and engine volume. And this parameter indicates the effectiveness with which the engine designer has used the engine material and engine packaging in the design process. The next one is correction for power and volumetric efficiency. This correction is needed when the engine is tested under non-standard air condition. The standard air condition is showing in this table, so it has a certain dry air pressure as well as water vapor pressure. So it means the air is wet air, and we learn about this wet air in Thermo 2 under psychrometric analysis. And this is the corresponding temperature of the standard air. And we use the orifice mass flow rate equation, so it should come from the fluid mechanic class. This mass flow rate is a function of the total pressure to the static pressure. So this is the mass flow rate through an orifice. And we have upstream total pressure and then downstream static pressure. So from this correlation, we know that the air mass flow rate here is a direct function of the pressure and the square root of the temperature, equation 2.38. So what does this mean? If we test the engine under different air conditions, it's mean different PO and different TO, then we need to apply the correction for the power and volumetric efficiency. And we know that the indicated power is proportional to the airflow. Therefore, if we want to increase the power, we need to add, for example, a turbocharger. So to increase the amount of the airflow and thus increasing the amount of the fuel for keeping the same air-fuel ratio. So for the power at standard condition, we can get it by multiplying the measure power by the correction factor CF, and the CF here is formulated by equation 2.40. So this is the standard pressure and this is the measured pressure at non-standard condition. And then for the efficiency, we have this correction, so equation 2.42. So it's mean that the ratio of the efficiency at standard condition to the efficiency at the actual condition here is a function of the temperature ratio to the power of 0.5. The next one is for emission. So this is the list of the pollution produced by the internal combustion engine. So we have NOx. So this is a group of NO and NO2, and then CO, especially for incomplete combustion. For sure, we have a CO2, and then this is unburned hydrocarbon, particulate, and soot. So this one is specific for a diesel combustion. And for the unit of this pollutant, it can be ppm or percent, volume, or mole fraction. So we have additional parameter here that is usually used when communicating the emission level with other people. So here we have specific NOx, so it's mean here the ratio of the NOx mass flow rate to the power. We have SCO, so this is for CO, this is for unburned hydrocarbon, and this is for the particulate. Depending on whether P here is indicated or break, so we might have I as NOx, or we might have B as NOx, similar for this one as well. The next one here is the emission index. So this is the ratio of the corresponding emission to the amount of the fuel flow rate. So equation 2.44. Next one is relationship between parameters. So in the previous slide, we have looked at one by one each of the engine parameter, and we can get a correlation between them. So for example, in this equation 2.45, so we have a brake power here as a function of the thermal efficiency. Some people call this fuel conversion efficiency. It's a function of the MA, so this is the mass of air, and this one is engine speed, this is lower heating value of the fuel, this is fuel air ratio, and this is the number of crank rotation per cycle. So you can see in here that the brake power is a direct function of the air flow or air mass. So once again, if you want to increase our engine power, so we need to increase the amount of air. One of the way to do that is by having a turbocharger. And this is another correlation of the brake power. In this case, we introduce this efficiency. This is volumetric efficiency. And this one, we have the density of air at the intake system. And this is the torque. So it is a function of the volumetric efficiency, engine thermal efficiency, this is brake, and then engine volume, lower heating value, and then air density at the intake system, this is fuel air ratio divided by 4 times pi. And the last one here is the correlation for the mean effective pressure, okay, a function of the engine volumetric efficiency and so on here. Once again, you don't need to remember this equation, so it will be provided for you in the exam. And this is another correlation. So in this case, we have a power divided by the piston area, and then for the last one here, we have a parameter of the mean piston speed. Okay, this is the mean piston speed of the engine. So from this correlation, we know that for having a max brake power, so we need to have a high volumetric efficiency and high intake air density. Okay, and then we need to have a maximum fuel air ratio that can burn in each cylinder to fully utilize air, because the function you see here, the power is direct function of fuel to air ratio. So high indicated fuel conversion efficiency to use a fuel chemical energy effectively. So this one is this one. And then we need to have low engine friction to minimize losses. So it makes sense, because if you can minimize the friction losses, then you can maximize the brake power. Okay, then we'll have a higher power, and we'll also have a higher mechanical efficiency. And from this last equation, you know that we also need to have a high mean piston speed. Okay, and this is consistent with high volumetric efficiency. So we will learn about the volumetric efficiency correlation with other parameters in chapter 6. Next one is looking at engine data maps. This feature is showing the map of the engine indicated efficiency on the left, and the middle is engine mechanical efficiency, and this one is the engine brake thermal efficiency, and all are a function of the engine speed. Okay, so let's start from the left feature here. So you can see in here that the engine indicated efficiency has a maximum one somewhere here. So it's create an island. And at the top here, this is the full load operating condition, this one, as well as this one. So it's mean along this line, the engine is operated under wide open throttle condition. Okay. And then going to the middle, so this is the engine mechanical efficiency maps. So it has a higher number when the engine operated under higher load and low engine speed. Okay, this one. And then for sure it will go to 0 as we go to the idle condition. So if we go to the idle condition, so it's mean there is no power outputted by the engines, and then mechanical efficiency is 0. And then on the most right side, so this is the map for the engine brake efficiency. So it has a maximum number at around this island. So this one is just the multiplication between this engine indicated efficiency and this engine mechanical efficiency. So the engine thermal efficiency is maximum around this island, and then another line here is showing the ISO line value. So it's mean the engine thermal efficiency is constant along this each line. So we will learn this engine data map in more detail, I think, in the last chapter of this class. This is the typical BMEP and torque as a function again of the engine speed, and this data was taken from Daimler Chrysler 4-cylinder inline. So the displacement is 1.6 liter. It has 4 valves per cylinder, so 2 for intake and 2 for the exhaust valves. And then the bore is 77, the stroke is 85.8 millimeters, and the compression ratio is 10.5. So you can see in here that the engine brake power increases with the engine speed, and this is the wide open throttle data. Okay, so it's mean it is at max load for each engine speed. So you can see in here that the engine power increases, and then it reaches the maximum one at around 6,000 RPM here. And this is the torque and PMEP plot. So let me put it right. So usually the plot will be like this one. Okay, so it's smooth like this one. Okay, and this deep, it is mentioned in the book that because they did intake tuning around this 3,500 RPM. So once again, if we don't have the intake system tuning, then the shape of this PMEP or torque profile will follow this line. Okay, and you can see in here that the max torque or max PMEP occurs around 4,500 RPM, and then the engine maximum power occurs around 6,000 RPM, and you can see also in here that at max power point, the brake or the brake mean effective pressure or the torque decreases and can be between I think 10 to 15% here. So this is the max one, and this is the PMEP at the max power point. So which is around 6,000 RPM here. And this is the performance data for diesel engine, I believe. This is the full load torque, PMEP power versus engine speed. So here, engine speed for turbocharged and intercooled direct injection truck diesel engine. Yes, this diesel engine. So this is from Hino K13C. So it has 6-cylinder inline. So with a 12.9 liter displacement. So this is a heavy duty application. So it can be for truck or bus. And the bore is 135 millimeter, the stroke is 150 millimeters, and the compression ratio you can see here 16.5. So it's much higher than the 1.4 spark ignited engine. And this is the brake power. So you can see there a smooth brake power increase, and then it reaches maximum one in here. And then the torque PMEP, see here it decreases continuously, and it has the minimum one in here. So depending on the relative size of the turbocharger to the engine, so the turbocharger might be able to increase the torque at low engine speed. So this is actually when we use a low size turbocharger. If we use a larger turbocharger size, then we might have kind of like this one. So this is just an example. Okay, so you might have kind of like this one. Oops, sorry. So I need to retro again. So it will lower the torque at the lower engine speed, but it can improve, it can improve the PMEP or torque at the higher engine speed. So this is the case when we use a larger turbocharger size. So we will learn this turbocharging in more detail in chapter 6. Next one is the engine benchmark. So we can use this parameter to do the engine benchmark. For example, like at maximum rated power, what is the mean piston speed, and then the BMEP, and then power per unit piston area. So this P over AP, and then we can also make comparison of the specific weight and specific volume. And then at all engine speed, so we can also make comparison of the brake main effective pressure, so PMEP, and then at all useful regime of operation, we can also make comparison of the PSFC or the brake specific emission. This table is showing the typical design and operating data for an internal combustion engines. So let's take a look at this one by one. So let's start with the small motorcycle. This is spark ignited engine. So I need to mention here that most of the engine are 4-stroke engine, except for very small size engine or very large engine size. So for the small motorcycle, usually the compression ratio is between 7 to 10, and this is the data for the bore and stroke. Sorry, this is the bore, and this is stroke to bore ratio, and this is the typical engine rotation speed, and this is the PMEP, and this is the power per unit volume, and this is the weight over power. And the last one here is the PSFC. So it has a very high PSFC, so it means the engine is less efficient. And then moving to the next one, so this is still spark ignited engine. This is for passenger cars, but this is NA, so it means it is naturally aspirated, so no turbocharger. This is 4-stroke, and then compression ratio here is between 10 to 12, and this is the typical bore size, and this is stroke to bore ratio, and this is the typical engine rotation speed, and then PMEP is higher compared to the motorcycle, and then it has also a better PSFC, so it's more efficient. And then if it is a turbocharged, so it's mean it's this line, this turbocharged. CAC here is charged air cooler, so it's mean we cool down the air after it is compressed inside the compressor of the turbocharger. So the goal is to have a a denser air, so thus it's improve the amount of the airflow and thus higher engine power. So for the turbocharged plus charged air cooler, this is 4-stroke engine. The typical compression ratio is between 9 to 11, and then the engine speed is between 5,000 to 7,500. And you can see in here it has a better PSFC than the NA. Okay, so it's mean I mean, if you want to translate it in easier way, is that it has a better mileage per gallon. And then next one is a larger engine but still spark ignited engine. This is for truck without turbocharger. It has now a higher PSFC. And the next one here is for a large gas engine. So it is 4-stroke, and then compression ratio is 9 to 12. Right now we are doing research on this large gas engine, so looking at slightly higher compression ratio, but we are still doing this research, and we are testing the engine now whether it's create NOx or not. And then this is the typical bore and stroke to bore ratio. Large engine usually has a lower engine speed. And then another important thing here, you can see in here that if you have a larger engine size, then it has a better efficiency, or it has a better PSFC. So this is because of the less important of the wall heat transfer. It's just one of the reason. Another one I think is the engine friction. So we'll learn this one in more detail in chapter 11, I think. Next one is Wankel engine. So this is a rotary engine, so not a reciprocating engine. So it has compression ratio around 10 to 1. This Wankel engine, as I mentioned in chapter 1, it is a compact engine. You can operate this engine at a very high engine speed, but it has a bad volume to chamber area ratio. Therefore, usually it has a worse efficiency. So it has PSFC of 280 gram per kilowatt hour. And then on the next part here, this is for the diesel engines. So starting from the passenger cars. So I think I saw Volkswagen has some variant of this diesel engine for passenger cars, and Chrysler, I think it has also. So usually the diesel engines has a higher compression ratio than the spark ignition engine. And this is the typical bore size as well as stroke to bore ratio. And diesel engines usually operate at slightly lower engine speed. But here another comparison that you can see in here, that the diesel engine has a higher weight to power. See here, compared to the spark ignited engine, this number is higher. So we need to have, so the diesel engine usually is heavier than the spark ignited engine, so that it has higher weight to the power output of the engine. But you can see in here that the diesel engine is more efficient, so therefore it has a lower PSFC. Last topic is the vehicle power requirement. So when an engine is driving a vehicle, it must provide enough power to overcome the resistance to vehicle motion, to accelerate the engine, and then to overcome the losses in the transmission and driveline. So this is the schematic of the force acting on a car while they are climbing a grid. So we have a aerodynamic track here, and then there is inertial force in case we need to accelerate this car. And because this car is climbing a grid, there will be a gravitation force as well. And there is also a friction. This is a rolling friction through the wheel, so Fr. So this means that the engine power should overcome all of this force. So the power required at the wheels to drive the vehicle is formulated by equation 2.51. So in this case, we need to overcome the friction force. This is aerodynamic drag force, and this is for accelerating the car. This is in case the car is climbing a grade, and this is in case we need to brake the car, and this is multiplied by the engine speed. So it is engine power multiplied by the combined transmission and the driveline efficiency. So then you will get the engine power. And this is the detailed data or detailed equation for each of the force. So first is here is the Fr. So this is the rolling friction force through the car wheel. So we have Cr. Cr here is the coefficient of rolling resistance. So the value usually between 0.01 to 0.02. And mv here is the mass of vehicle. So this is the curb mass plus the payload. Okay. And then g is the gravity acceleration. And then Fd, so this is the aerodynamic drag. This is a function of the air density. Cd is the drag coefficient. So the value is between 0.2 to 0.5 for cars. And they also mention here that the average is usually 0.33. And then AV here is the frontal area of vehicle. So it can be estimated as 0.9 times vehicle width times vehicle height times the vehicle width. And then FA is the force to accelerate the car. So this is the mv, mass of vehicle or mass of the cars, times the acceleration. And Fg here is in case the car is climbing a grade. So this is mv times g times sinus of alpha. So this is the inclination angle. There is another parameter which is called a load power. So this power is used to overcome the tire rolling resistance and the aerodynamic drag of the vehicle. So it means we test this car on a level road and at steady speed. So it means no acceleration. And this is used for testing automobile engines. So we have equation 2.53 here, where it's contain only the rolling resistance as well as the aerodynamic resistance. And the next two equation here is just to help us to calculate this power in different units. So this is SI unit, this is British unit, as a function of certain parameter here with a certain unit. Okay, once again, you don't need to remember this equation, but you need to know when do you need to use this equation. Okay, we have completed this chapter 2 presentation. If you have any question, you can ask me in the next class meeting. Thank you.